Hey guys, in this video we're going to start getting into the next round of trig identities. Now that we've worked with the first set for a little while, we're going to start introducing a few more. In this video we're going to go over the sum and difference identities. So grab a calculator out for these first few problems and we'll get started. These first few problems are trying to point out a very common misconception that people have about adding trig values and adding angles. Number 1 shows us this equation cosine of 75 degrees equals cosine of 45 plus cosine of 30 degrees. Let's take this 75 and break it up into 45 plus 30. So then the equation would look like this. And this is basically asking, like, does the distributive property work for trig functions? Can you take 45 plus 30 degrees and just distribute this cosine in and get cosine of 45 plus cosine of 30? So the directions say use your calculator in degree mode and determine if the following equations are true or false. So they gave us this equation, but we're not sure if it's true or false. That's why I put this little question mark above it. So make sure your calculator's in degree mode and start typing this in. So cosine of 75 degrees, make sure you get 0.2588. For cosine of 45 degrees, you should get 0.7071. And for cosine of 30 degrees, you should get 0.8660. And it makes sense that all of these are positive numbers because all of these angles are in the first quadrant, and that's where we have positive x or positive cosine values. But of course, this equation is not true at all, right? If you take 0.7 something plus 0.8 something, there's no way you're getting 0.2 something. So in this example, you can't take cosine and distribute it into these parentheses. And I'm even going to go back up here and put a slash through that equation as well because this is not true. And I think we're going to see the same thing in example 2. We've got sine of 15 degrees and then sine of 45 minus 30. So if you think of 45 minus 30 being 15 degrees, you could rewrite the equation as like sine of 45 minus 30. And then again, this problem is just asking, can you distribute sine into these parentheses and get sine of 45 minus sine of 30? Does that hold true? So again, start typing this into your calculator. Check that you get 0.2588 for sine of 15 degrees. Sine of 45 is the same as the cosine value. That was 0.7071. And sine of 30 is 0.5. And of course, we're used to getting these values off of our special triangles, but since we're dealing with an angle like 15 degrees, and I don't know how to evaluate that yet, that's why we were just using our calculator, just to compare these values. Now, this one's a lot closer to being true. If you take 0.7 something and you minus 0.5, you do get close to 0.2, but it's not exactly this. So this one's false as well. So you can't take angles and add them together and just say that's the same as the cosine of those two angles together. And you also can't do the same thing with subtracting. You can't say sine of 45 minus sine of 30 is the same as sine of 15. But there are these little formulas, or in this case, these sum and difference identities that help us do things like take the cosine of 75 degrees. So here's the 6 sum and difference identities, and they're kind of confusing the way they're written. First of all, I don't know who chose u and v to use for the variables because they look so similar. So just be careful when you're writing and reading these that you are correctly writing u or v. So in the first problem we looked at, we had cosine of two things being added together, or I kind of rewrote it that way, right? We had cosine of 45 plus 30. And we saw that you can't just distribute the cosine into the 45 and the 30. But there is a way to do this problem. You just have to use this formula. Okay, so cosine of u times cosine of v. And u and v are just these two angles. So that means the first thing I'm going to write is cosine of 45 times cosine of 30. And when you're typing this into your calculator, just make sure that you put parentheses around these things just so that it doesn't think that this cosine is like part of the inside of this cosine or something like that. And then we have to subtract sine of u times sine of v. So sine of 45 times sine of 30. And if you want to verify that, just type this into your calculator, right? So type cosine of 75 in, see what that is as a decimal, and then type this entire thing in. And you'll see that you get the same exact thing. So these 6 identities allow us to now take the sine, cosine, and tangent of a lot more angles that we haven't worked with before. So far, we've only ever been able to work with angles that come from our special triangles. So like any kind of multiple of 30 or 45 or like 60 or 90. And those are the angles we worked with on the unit circle. But of course, there's lots more angles. And now we can do things like work with an angle like 75, or any combination of these angles. And I want to show you something else you can do. You can actually sometimes use trig identities to prove other trig identities that you've seen before or maybe haven't seen yet. And we've seen ones like this, like sine of pi over 2 minus theta. And since that comes from the cofunction identities, we said that that was equal to cosine of theta. And you can actually prove that with this trig identity. Okay, so if you have sine of u minus v, it tells you to take the sine of u times the cosine of v. Okay, so sine of the first angle, so sine of pi over 2 times the cosine of v, so cosine of the second angle, and the second angle is just theta, and then subtract cosine of u times sine of v, so minus cosine of that first angle, so pi over 2, times sine of v, so sine of theta. So I just took the left side of that equation and expanded it into all of this. And apparently that's supposed to just equal cosine. And here's why. Because some of these angles we can't do anything with, like cosine of theta and sine of theta are stuck. We can't evaluate those. But sine of pi over 2, I can evaluate that. So if you think on the unit circle, pi over 2 is up here, and the sine value is the y value. So this is the point 0, 1. So that means sine of pi over 2 is 1. So this term, sine of pi over 2 times cosine, is just like 1 times cosine of theta. And then over here we have minus cosine of pi over 2 times sine. Again, pi over 2 is up here, and that was the point 0, 1, and the cosine is the x value. So if this is 0 times anything, this is all just going to cancel out. So we'll say when we evaluate this term that is just minus 0, and then 1 times cosine minus 0, that's just cosine. So this is actually the first proof that we worked through. And we were able to prove this cofunction identity using the sum and difference identity. Let's take a look at a few more examples. This one just says find the exact value of the expression, and in part A we have cosine of pi over 4 plus pi over 3, so we have a sum of two angles inside a trig function, and in the second example we're just adding two trig functions together. Again, this problem is just trying to hit home the fact that you can't just distribute cosine into these parentheses and come up with cosine of pi over 4 plus cosine of pi over 3. But this one says find the exact value, so I'm not just going to type this into my calculator because that would just give me a decimal value. Okay, so I have to show my work and use that identity that we just learned. So I'm going to use the identity cosine of u plus v equals cosine of u times cosine of v minus sine of u times sine of v. In other words, my angle u is pi over 4 and my angle v is pi over 3. So we should draw those angles out because we're going to have to find the cosine and sine values of them. So pi over 4 is in the first quadrant, that's a 45, 45, 90, and I'm going to label these side lengths as well. And then we'll do the same thing, so pi over 3 also in the first quadrant. And I'm also going to rewrite this, but plugging in pi over 4 and pi over 3 for the u and v angles. And now we can start evaluating all of those. So cosine of pi over 4 is the square root of 2 over 2. Cosine of pi over 3 is 1/2. So I'm just taking the x values because we're looking at cosine. And then minus sine of pi over 4 is the y value, so square root of 2 over 2. And sine of pi over 3, again the y value, that's square root of 3 over 2. So we have two fractions being multiplied together, two fractions being multiplied together. So I'll do that first. Square root of 2 times 1 on top is just the square root of 2, and on bottom, 2 times 2 is 4. And then over here we have the square root of 2 times the square root of 3, and you can multiply those together, so that's the square root of 6 over 2 times 2 is 4. Okay, so now we have two fractions being subtracted, and they do have common denominators already, so I can just go ahead and subtract them. We've got square root of 2 minus the square root of 6 all over 4. And that's your final answer. That's the value of the cosine of pi over 4 plus pi over 3. Now if you compare that to cosine of pi over 4, which is just the square root of 2 over 2, plus cosine of pi over 3, which is 1/2, again we have fractions being added together, and they already have common denominators, so I can just put them together, and we've got the square root of 2 plus 1 over 2. And that value is not the same as the square root of 2 minus the square root of 6 over 4. So just to clarify what we did over here, we took the cosine of some angle. It looks like two angles, pi over 4 plus pi over 3, but if you add those two values together, let's just do that over here, pi over 4 plus pi over 3. Well, I need to get common denominators, so I'm going to try to get 12 in the bottom. So I'll change that to a 12, which means I had to multiply that by 3. This one I have to multiply by 4. All right, so now I can add these together, and this would be 7 pi over 12. Okay, so we really found the cosine of 7 pi over 12. And that's weird because that's not an angle that we've ever worked with before. I mean, it is on the unit circle, but it doesn't come from any of our special triangles. So all of these sum and difference identities open up a whole wide range of more angles that we can work with. Let's try another example. Again, this one says find the exact value, so I'm not going to use my calculator and just plug this in. I'm going to write out the work using those identities. So we've got sine of one angle plus another, and that identity looked like sine of u times cosine of v plus cosine of u times sine of v. So again, the two angles I'm working with are 2 pi over 3 for u and 3 pi over 4 for v. So I'll draw out u over here, and I'm going to label it as angle u, and 2 pi over 3 is in the second quadrant. This would be negative 1/2 on the x-axis, positive square root of 3 over 2, and 1 for the hypotenuse. And then my angle v, this 3 pi over 4, also in the second quadrant, but this has square root of 2 over 2 and negative square root of 2 over 2. Again, I'm just going to rewrite this quickly, but replacing u and v with 2 pi over 3 and 3 pi over 4. And then it's just a matter of getting all of these values from the special triangles that we drew out to the left. So sine of 2 pi over 3 was this tall y value, that was the square root of 3 over 2. The cosine of 3 pi over 4 was negative square root of 2 over 2. So negative square root of 2 over 2. And I'm putting that in parentheses because I don't want it to look like I'm subtracting these. I am multiplying them together. And then plus cosine of 2 pi over 3 is negative 1/2. So again, I'll put this in parentheses. And then times the sine of 3 pi over 4, which was the square root of 2 over 2. So here we have the square root of 3 times negative square root of 2, so negative square root of 6 over the bottom, which is 2 times 2 is 4. And then over here, we've got 1 times the square root of 2 on top and 4 on bottom, and this is being subtracted. So this answer is going to be the negative square root of 6 minus the square root of 2 over 4. And it's okay to multiply radicals together like we did up there, but you can't add or subtract them together down here. So there's no way to simplify this really, so that is our final answer. Examples 3 and 4 are a little bit different. This one says write the expression as the sine, cosine, or tangent of an angle, so just one single angle. And it doesn't say evaluate it, so I'm not going to plug it into my calculator. I'm not going to find these values and get a value as an answer. It just says write the expression as the sine, cosine, or tangent of an angle. So if you look at sine times cosine minus cosine times sine, like just look at the general structure of the problem. That structure, sine cosine minus cosine sine, comes from sine of u minus v. And again, if you just substitute the u and the v with these two angles, you'd get sine of, and then 230 minus 30, which is just the sine of 200 degrees. Now, 230 degrees does not come from a special triangle angle, so this isn't a problem that we would have been able to do using special triangles, but it does show you how you can take a complicated expression like this and simplify it down to just one thing, like sine of 200 degrees. And we can do the same thing here. We have this huge mess, tangent of 325 minus tangent of 86, yada, yada, yada. If you look at the bigger structure, it's tangent of something minus tangent of something, and then on bottom we have 1 plus tangent times tangent. So again, look through those 6 identities, and you'll see that this matches up with tangent of u minus v. So I'll take out the u and the v and substitute in 325 and 86, and that would give you tangent of 239 degrees. So not only can we evaluate more angles that we haven't worked with before, but we can also take complicated expressions like this and simplify them down. These next few examples are just having us create these new angles that we haven't worked with before using combinations of 30, 45, and 60, or sometimes in radians, pi over 6, pi over 4, and pi over 3. 75 degrees might be kind of an easier one. We actually already kind of worked with this, so 45 degrees plus 30 degrees equals 75. But negative 285 degrees is a little bit tougher. The fact that we have a 5 in the end tells me that we need to use a 45 at some point. So first I'm going to add or subtract 45 degrees from this angle and just see what other angles are around it. Okay, so if I were to add 45 to this, we'd actually have negative 240. And 240 degrees is an angle on the unit circle that we can use special triangles for. So if you think going in the negative direction, this would be negative 180, and then I would need 60 more to get to 240. So negative 240 would be like this. And of course, positive 45 is just in the first quadrant. So to answer this problem, they're just looking for us to write negative 240 plus 45. That's how we're taking this angle negative 285 and breaking it up into these two angles. But we're not just arbitrarily picking any numbers for our angles, we're picking angles that come from special triangle like reference angles on the unit circle. With 13 pi over 12, I know I'm going to have to add two fractions together, and at first I'm just going to think about these being over 12. So like what over 12 plus what over 12? And I'm trying to add to 13 pi over 12. So here's the trick. For one thing, these two numbers will have to add to 13, but also they'll need to be something that I could simplify these fractions down because I'm not used to working with pi over 12 type angles. So I'm going to think of some numerator that I can put in the top that would simplify over this 12. So if I put like 6 here, well 6 plus what is 13? That would be 7. Okay, well 6 pi over 12 simplifies, but 7 pi over 12 doesn't, so that's not going to work. So what if I did, well like 5 pi over 12, that's not going to simplify either. So 5, 6, and 7 are all out. What if I tried 4? Okay, 4 plus what would be 13, and that would be 9. Okay, so 4 pi over 12, that would simplify to pi over 3 if I just divide the top and the bottom by 4. And then over here, I can divide the top and the bottom by 3, and that would be 3 pi over 4. So that worked out because 4 pi plus 9 pi is 13 pi. So this is a true statement. And then we were able to simplify both of those angles into something that I could take like the sine or cosine or tangent of because these are special triangle angles. Let's do the same thing for negative 7 pi over 12. And again, I'm going to think of this as a negative angle minus another angle. Okay, so if you think of something pi over 12 minus something pi over 12. And in order to make 7, if I were to just put 3 and 4, right, so negative 3 minus 4 is negative 7, and then just look, can I simplify both of these fractions? Right, so 3 pi over 12 would simplify to pi over 4, and 4 pi over 12 would simplify to pi over 3. Okay, so again, the numerators worked out, they created the 7 pi over 12, and both of these fractions were able to simplify into angles that I've worked with before. Now, just a quick side note about a problem like this, if you had cosine of negative pi over 4 minus pi over 3, and you wanted to use those sum or difference identities to evaluate this, just be careful about, are you thinking about this as like a negative angle minus a positive angle, or are you thinking of it as a negative angle plus a negative angle? Personally, in a situation like this, I prefer to think of it as a negative angle, so negative pi over 4 would be here, and then plus another negative angle. Okay, so negative pi over 3, again, would be in the fourth quadrant, just be the tall, skinny triangle. But I'm really thinking of this as cosine of negative pi over 4 plus negative pi over 3. And I'm doing that so that I can use the cosine sum identity. Okay, so cosine of u plus v. And that just helps me keep things organized as I'm working through the problems. Actually, speaking of cosine of u plus v, that's our next problem. Okay, so we don't know what u and v are. If I back up and we read the directions, it says find the exact value. So again, no calculators, you got to show your work. Of the trig function, given that sine of u is 5/13 and cosine of v is negative 3/5. Okay, so honestly, I'm going to latch onto this because this seems like the easiest fact so far. Both of these angles are in quadrant 2. I don't know what either of these angles are, but I'm going to draw them both in quadrant 2. So here I'm going to say that's angle u, and this will be angle v. And I'm just drawing kind of generic triangles. Now it says the sine of u is 5/13. Okay, so here's my angle u, and I'm going to label the sine as 5/13, so opposite over hypotenuse. And that makes sense because it's positive, like sine is positive, those are all y values, that's all good. And then it says the cosine of v is negative 3/5. So in this angle, the cosine value is negative 3/5, and again, that makes sense because this is a negative x value. Now they don't tell us the third side of either of these two triangles, so I'm just going to use the Pythagorean theorem quickly and figure that out, because I think I'm going to need to know that when I'm doing these problems. And then over here, you might recognize that 3, 4, 5 is another Pythagorean triple, so these worked out pretty well. Sometimes you'll end up with square roots for some of these side lengths, and that's totally okay. Alright, so now that we have everything drawn and labeled, let's start evaluating this. So I'm going to use that identity, cosine of u plus v is the cosine of u times the cosine of v minus the sine of u times the sine of v. And then we just have to get all of those values from the triangles that we just drew. So cosine of u would be negative 12/13. Cosine of v is negative 3/5. And since there's all these negatives, I'm putting this in parentheses. And then we have minus, okay, so now the sine of u is the y values here, so 5/13. And sine of v is 4/5. And again, we're multiplying those together. So when I multiply these two fractions together, negative 12 times negative 3 is positive 36, and 13 times 5 is 65. And then in the second term, we've got 5 times 4 on top, which is 20, and this is being subtracted. Again, on bottom, 13 times 5 is 65. So we've got 36 minus 20, and that would be 16/65, and that fraction can't be simplified, so that's our final answer. Example 6 actually won't take hardly any work for us at all. It's asking for the secant of u plus v, and we don't have any identities for those. But all we have to do is just know that this would be the same thing as 1 over cosine of u plus v. And we just found that value, right? We found cosine of u plus v in that last problem, and this is just going to be the reciprocal of it. Okay, so we got 16/65 before. This one's going to be 65/16. And our last problem is just tangent of u minus v. Okay, so we had to do one tangent example just because these are the crazy ones with all the fractions and all that. So this one would be tangent of u minus tangent of v over 1 plus, and then the two tangent values multiplied together. And this problem is using the same information from before, so I'm just going to copy those triangles quickly. And then we just have to find all these tangent values using those triangles. So tangent of u would be opposite over adjacent, that would be 5 over negative 12, and then minus tangent of v, and then over 1 plus, and then those two tangent values multiplied together. So 5 over negative 12 times 4 over negative 3. So let's just be careful with all of these negatives. The first thing is when we multiply these negatives in the bottom together, those will both just become positive. So we've got all positives in the bottom. And then up here we've got these fractions with negatives in the bottom, and it doesn't matter that the negative's down there, right? Like I could just get rid of that and put it out front. But then we're subtracting a negative, and that would be like adding. So let me just rewrite all of this. We've got negative 5/12 plus 4/3 over 1 plus 5/12 times 4/3. And all of a sudden it's not that bad anymore. We do have to get common denominators in the top though. So I need to make this a 12, which means I need to multiply the top and the bottom by 4, which means that becomes 16. All right, so negative 5 plus 16 would be positive 11 over 12 over, and then on bottom, here we're just multiplying these fractions together. So I'll write the 1 plus in front, and then 5 times 4 is 20, and then 12 times 3 is 36. So we'll just keep working with these fractions. I'll leave the 11/12 on top alone, and then on bottom, I'm going to think of this 1 as 36/36 plus 20/36. All right, so that gives me 11/12 on top over, this would be 56/36. And then finally, dividing these two fractions is just the same thing as multiplying by the reciprocal of the bottom, so times 36 over 56. All right, so the 12 and the 36 can simplify if I cross that out and make that a 3. And neither 3 nor 11 can go into 56, so this can't be simplified any farther. So I'll just multiply these together on top and get 33 over 56, and that is your final answer. So there's really just like two main parts of these problems, right? So draw the triangles out, which we already did in the last problem. I just copied those values down. And then once you have those triangles, just fill in those values. And unfortunately, the tangent problems require a little bit more work because we're dealing with so many fractions. But at that point, you just have to be careful with your arithmetic as you're simplifying those values down.